on to this. Okay, just people waiting outside. Okay. For them to come. Okay. Right.
Okay, we'll now get started again. The final part of this workshop today with Abhinav Gupta. Abhinav is a professor at the Robotics Institute at Carnegie Mellon University. His research focuses on scaling up learning by building self-supervised, lifelong, and interactive learning systems. Specifically, he's interested in how self-supervised systems can effectively use data to learn visual representation, common sense, and representation for action in robots. Today, he will be giving a talk on generalization via scaling robotics. Let's give him a warm welcome.
Thank you. All right. I guess we are all seeing this huge revolution happening around us in the field of both language and vision. And if I have to pinpoint like what has been the recipe behind making these large language models or large vision models work, I would say it's scaling. If like one factor I had to choose, scale has been a big factor in making these models work. But when it comes to scaling in robotics, it's not so trivial, right? Because in language and vision, you have the data available on the internet. For example, there's Wikipedia and so many websites where you can harness the language data. Similarly, for vision, there's so many images on the web and YouTube that you can harness and train your large-scale model. But in robotics, there's no data set that you can download and start training your large-scale robotics foundation model. Not only there is no data, hardware is slow and sometimes super expensive. So it's really hard to collect trillions of examples if you have to collect them on the hardware itself. And because there's never been any large-scale data, I would argue there are not even any algorithms. If let's say tomorrow magically a trillion examples appeared on the internet, I'm not 100% sure if you can just train a transformer model with 1 trillion robotic examples, and the robotics foundation model would be learned. And so in the last decade or last 5 to 10 years, there has been a lot of efforts in trying to scale up robot learning. And so one of the first efforts was from our lab itself, where we basically tried to collect large-scale data on the hardware itself. And so this was a self-supervised robot that we built at CMU, which will collect data 24/7, trying to do random grasp and see if the grasp was successful or not. Following it, Google did an arm farm as well, which was like scaling this up to 15 robots and try to collect even larger scale data and so on. But as I said, the problem with collecting data on the physical hardware is that you cannot go faster than real time. And so even if you had hundreds of thousands of robots deployed and collecting data 24/7, it will take a long time before you can get enough examples to train large scale foundation model. The second approach, which a lot of people are trying nowadays, is teleoperation based approach. Here, a human tries to control the robot and collect examples. And now because a human is controlling, you get much more positive examples. You do not have lots of negative examples and so on. Even teleoperation is difficult and slow. But more importantly, even teleoperation is not scalable. For example, the Google's RT1 and RTX effort collected 1 million examples over 2 years, right? And if you think of the scale that we need, we don't need million examples. We don't need billion examples. We need trillions of examples. Like the current LLM models are working with 30 trillion to 100 trillion examples. Even if the whole population of Earth becomes contractor and start collecting data with teleoperation, it will take decades before we can get to a scale where we can learn large-scale robotics foundation model. The third approach is maybe to scale by simulation. And this idea has existed in the field also for long, right? The idea is you can scale up the data collection effort in simulation and then train your large-scale foundation model in simulation. And hopefully now after that, you can train a sim to real transfer model itself. Now, there are lots of issues with the simulation as well. For example, the domain gap. There's still a big domain gap between simulation and real. Not only that, the diversity is still limited in the case of simulation. Building each scene can take thousands of dollars. And so it's unclear how would you learn on diverse examples. The core issue in all these existing models is that we need to collect interaction data. And collecting interaction data is really, really hard. And so in this talk, I want to explore that can we actually reduce the active data, the interaction data that is needed to learn the foundation models themselves. Now, again, I want to remind that in the last decade, a lot of people have focused on this idea that, oh, babies learn by interacting with the world. So let's try to collect large-scale interaction data to train our foundation models. But this is an incomplete picture, right? Because babies are not only interacting with the world, they're also observing the world around them. Like what's happening around them, they're observing their parents, they're observing their teachers. And based on that all information, they also learn. So in this talk, I want to explore how we can use passive data, the videos on the web, the images on the web, to basically scale up robotics, large-scale learning in robotics. And so the question I want to investigate is how do we use passive data in policy learning itself? Now, to understand that, let's take a step back and see what does policy learning involve. So if we are trying to learn a robotics foundation model, our goal is, given the pixels as input, we want to predict actions, like what actions should robot take given that pixels. And this model has to do 3 things. First, it has to learn the visual representation. Like this is the abstraction that is required visually. For example, the silver and the gray laptop should be put in a similar space in the visually because they behave similar. Next, the model also has to learn dynamics, right? So for example, this is an articulated object. So if you apply forces, how will it move? This kind of dynamics has also needs to be learned by the model. And finally, because it's a robotics foundation model, it has to spit out actions. It has to learn the policy, which is what action should the robot take to achieve a goal. Now, because you have to learn representation, dynamics, and policies, you need lots and lots of data to learn this model. And so here we want to see, can we actually use the visual data to actually factorize some kind of learning and basically reduce the requirement for learning the large-scale models. So in the first part, I want to explore how we can use pre-trained representation learning to reduce the active data requirements. So again, taking a step back, we want to learn a policy which given a pixels will give actions. But instead of learning one neural network, if you divide it, factorize it into 2 parts. The first, given the pixel, learns an intermediate representation, and the second model, given an intermediate representation, learns the action. And so the first part can focus on learning the visual representation. Like, how should you represent pixels so that you can actually do dynamics, learn dynamics on top of it, or learn action models on top of it. And then the second model learns dynamic and action. The hope is by dividing it into 2 parts, most of the lifting, the learning will be done by the first part, the visual representation, and then the dynamics and action can be learned with much less active data in this scenario. And the first part is very scalable in pre-training because you can use all the images, the passive videos to learn the visual representation that would be useful for robotics. And so in first part, I want to explore how we can pre-train visual representation for robotics and then use small amounts of data to fine-tune and learn a action model on top. Now, again, in the past 4 or 5 years, there has been a lot of work in trying to learn representations for robotic tasks, both in the space of gathering the large-scale data sets and training models itself. So, for example, EI4AS is one of the biggest effort in trying to collect manipulation example where humans are manipulating different objects, and this is collected in the first-person video data itself. And the approaches that have been used are mostly self-supervised approaches, for example, mask autoencoders and other self-supervised learning approaches as well, and so on. But one question that we wanted to ask is, if you use off-the-shelf self-supervised approaches with this EI4AS data, does it learn robotic representations or does it learn something completely different? And so in the first paper, we kind of try to explore what kind of representations are learned if we use off-the-shelf self-supervised learning approaches with more manipulation data. Are they useful for learning robotic representations or not? So to do this, we did a very simple experiment. We chose 5 different data sets. Some of them are more relevant to the manipulation task, and some of them are completely irrelevant to the manipulation task. So for example, we chose ImageNet, which is irrelevant to the manipulation. It has basically all the random images for different categories, 1,000 categories. Then there's 100 days of hands. This is more manipulation-driven data set, but collected from YouTube. EI4AS is much more top-down effort and structured effort in collecting manipulation data sets. Then there is kinetics, where there's lots of actions, but they might or might not be manipulation-driven. And finally, there's RobotNet, which is very much robot-driven data set. It's closest to robot data that you would need to train a model. We take these 5 data sets and then learn a mask encoder on top of it. And then we want to see if these learned representations are useful for robotic tasks, for example, in simulation, as well as in real world. And in the real world, the tasks that we evaluate are pouring, block stacking, and toaster. And so in the first experiment, we just did this, train these mask autoencoder, and then fine-tuned it with some of the collected teleop data. And we basically see what kind of performance you will get. And so if you notice here, that ImageNet-based pre-trained representation gets the best performance compared to EI4AS and RobotNet. And that is kind of surprising, right? I mean, you have a data set which is much more suited for manipulation tasks, yet a representation learned on it is not learning that good of a representation compared to ImageNet. Not only that, there have been like papers like VC1 and MVP, which are basically representations which are more specific for robotic manipulation. And this ImageNet representation even learns better than that. And so what is happening is these off-the-shelf self-supervised approaches are still learning texture-based features and so on. And they are not useful for robotic tasks at all. And so for the first, so in this case, ImageNet works better because ImageNet has much more diversity. And so it kind of becomes much more effective for visual pre-training. And then the self-supervised approaches are not effectively taking the juice out for learning robot representation learning. So then we want to explore how, if EI4AS is such a great data set for manipulation, how can we extract the juice out of it to train a good representation for robotics? And so in the next paper, what we do is something very simple. Instead of trying to focus on the whole image, we fine-tune the model, pre-trained model, for a task which is called affordance fine-tuning. Here, the model has to predict what are the contact points, what are the hand poses, and what are the active objects in the video it's also, apart from doing the pre-trained representation. And the hope is, if the model has to predict contact points, hand poses, and so on, it can now focus on the right pixels to learn the representations. And so with this simple experiment, we first take the EI4AS data, run a hand tracker on it, and predict the contact point, hand poses, and active objects. This becomes the ground truth data for the training. And then we basically take the pre-trained model and fine-tune it with this task of contact, hand pose, and active object. And we are not going to train all the layers. We will keep few layers frozen, and we only learn the layer norm layer on top of it. And again, with this simple task, like focusing on these contact and hand poses, we see that the affordance prediction improves the robot representation learning a lot. Even like the ImageNet features, Dino features, and all these features become much better with this affordance prediction task because it's now focusing on the right pixels. And more importantly, EI4AS now has the best performance because this approach can take out the juice for the robot representation learning. And not only it basically works on the EI4AS data, egocentric data, but it also works on the front camera and also different kind of hardware as well. Just to show you some examples, here are some of the examples of like grasping with a dexterous hand. Here's another example of grasping and then putting objects inside the pan with this kind of a pre-trained representation. Okay, so this is the first part where we try to pre-train representations using the large scale data, the images and the videos on the web. But can we do better? Can we actually learn dynamics also from these videos, which will make even the task of learning robot action even simpler? So again, taking a step back, we want to learn policies that given pixels learns representation, dynamics, and policies, right? And now we are going to divide the model into two parts. The first part, given the pixels, learns an intermediate representation, which has both representation learning, also the dynamics learning. And then once in the second part of the model, once we have learned the representation and dynamics, we learn the action model, which maps these intermediate representation to the final action. And the first part is scalable. It can be learned from videos and so on. Just to remind you, this is very simple, similar to the world model idea. The first part is actually a world model that we are learning. And then the next part is the action that we are learning, predicting from those world models. And so the way we are going to achieve this is using the factorized policy. So instead of learning a policy that given a pixel maps to action, you're going to divide the policy into two parts. The first part is the visual interaction plan. Here, given the initial image and the final goal, the visual interaction plan predicts in some visual space how you would achieve that goal state in multiple steps. And then the robot execution plan is a way to convert that planned interaction in visual space into robotic action. Just to explain it better, so here's a visual interaction plan. So for example, given an initial image, how should the segment of a hand and segmentation of the active object move or change over time so that you can reach the goal state? So in some way, this is a plan. You're planning in your mind of how it should look visually if you're doing these actions, if you're attaining this goal. And once you've planned using the visual interaction plan, you can map it to the robotic action either directly. So here you can assume the rigid transformation, there's only one object moving and directly convert them into actions. Or you can collect a small robotic data set, which has both the visual interaction plans and the map actions, and learn a mapping between visual interaction plans to robot actions. So in this talk, I want to explore three different way of representing visual interactions. In the first one, I want to explore the segmentation as a way to represent visual action, visual plans. So given the initial image and the final goal image of opening a microwave, how should the segment of the hand and the microwave move such that we can achieve this task? In the second one, I want to explore how we can how the track points move for going from initial image to the goal image. And finally, we want to explore if we can use the off-the-shelf generative video examples to actually train. So given the initial image and the task being pick up tissues from the box, you can actually generate a video from off-the-shelf video generator. And that could be a plan that is generated by the model. And now you convert this plan into the robot actions. So let's start with the first one, where we are using segmentations as a way to predict the plan. So again, the policy is going to first predict how the segment should move, both the hands and the active object. And then we are going to convert that visual interaction plan, this segmentation, into robot actions by learning a mapping model. So just to look at the first part, how do you learn this, the visual interaction plan? So given a goal image and an initial image, your goal is to predict the segmentation. So you learn a diffusion model, which basically takes in these noise images and factor and the initial image and goal image and predicts these segmentations of active object and the hand moving in the segmentation space. And then you have a small data set where you have these interaction plans as well as the robotic way of achieving those tasks. And you learn a mapping between the interaction plans and the robotic action by learning a transformer which maps these segmentation videos into the robotic actions themselves. And so we are going to do the evaluation across different levels of generalization. Mild generalization is the same objects that you were seeing in the training examples, but lighting is changed or some minor changes are there here, like maybe some position changes are there and so on. Standard generalization is completely unseen object instances. Categories remain the same, but object instances are different. Compositional generalization is where the combination of action and object has never been seen before, but this object has been seen with some other action and so on. And last is the type generalization, where a completely new object category that was never seen before, a completely new action category that was never seen before, and now we are going to test on this task itself. And so we are going to use in two setups. First, the tabletop setup, and then this setup where the Franca is installed on a wheelbase. And this is Homanga who's sitting here and trying to move around this robot in the Facebook kitchen, trying to collect data. We did not train it in this kitchen. It's completely new kitchen on which it was not trained. And so here are some of the initial examples of these things. So given the initial image of the microwave, this is the predicted plan, and here is the robot action at the bottom of how the robot will go and open it. For the toaster, given the original image and the final image, the plan is again predicted with the segmentations, and then here is the robot action, which conversion plans into robot action. But my favorite ones are the strong generalization ones, which are kind of actions and objects that we've never seen before. Again, these are the tasks which are not seen before in any of the training data. That is one of the small shortcomings of the current teleoperation behavior cloning approaches. Like you cannot go far from the training examples. You have to be in the very close distribution. Whereas by this factorization, a bulk of the learning effort has been placed on the visual part. And so now you can basically, using even small amount of robotics data, try to get these strong generalization results, which were not at all in the training data examples. Here are some more examples of standard generalization and some in the wild examples, like in the kitchen that we never saw before. And now basically robot doing all these different tasks of closing drawers, moving around objects, putting things in the microwave and so on. Okay, so that was the first part where we were using segmentation as a way to put the visual interaction plan. Next, we wanted to try something more which does not have this idea of embodiment. Like in the visual interaction plan with segmentation, we assume that there's a hand and there's an active object. But in this one, we want to use track points, like dense track points, to represent the changes. There are two benefits of this. First, once you know the track points, that the track points are moving like this, it's very easy to convert them into robot action under the rigid transformation assumption. That only one object is moving, and if track points are moving like this, you should apply a force from robot in this direction. So that was, and the second reason you want to go is because you're not making any assumption of how many objects are there, what object is, and so on in this plan. And so the approach is simple here. Again, we first learn the given an initial and goal image, how should the track points move to go from initial image to the goal image. And then we are going to map these track points into robot action. First, we are going to try an open loop policy, which is like rigid transformation, like assuming that there's a rigid transformation, what action should robot apply to get this rigid transformation? As the results will show, the open loop does not work that great because it will miss the original. So we also learn a residual policy on top using that small data set that we collect on the top. And so here is how the approach looks like. Given the initial image and the goal image and the noisy track points, we used again the diffusion model to predict the track points, how the track points will move for achieving this, from going from this initial image to the goal image. And once we have these predicted track points, we are basically going to plan with an open loop. So you can see with an open loop, even though it has to open the drawer, it misses the handle completely. Whereas in this jug, it basically is not able to grasp the jug and it misses the jug as well. So we learn a residual policy on the top, and the residual policy is learned with this again with this data set. So given the track points, predicted track points, and the open loop plan, the goal is to predict the residual actions, which will help us to achieve the goal. And so now with this residual policy, you can see now the robot is able to grasp the drawer and it's able to pull the drawer. Similarly, the robot is able to now grasp the jug and is able to pour from the jug as well with this residual correction. Here are more examples of these different actions tried with this open loop and residual policy. You can again see that these are very wide, diverse examples. In all these cases, the navigation is done with teleoperation and the model is only doing the manipulation part. And again, we are showing lots of different examples, not just like one or two, but lots of different categories of examples, manipulation examples. In terms of numbers, if the top row shows the behavior cloning, the segmentation visual plan actually works pretty good in the mild generalization case when you are not changing lots of things. But as soon as you go into harder generalization cases like type generalization and so on, the segmentation based approaches starts to fail because it has not seen enough data. Whereas both this kind of predicting these dense feature points, now it's able to predict most of the heavy lifting in the prediction is done by this dense feature points. And so converting them into actions is much simpler for the robot model, and it basically converts them into actions. And we can get pretty good results there. Here are some more examples of what kind of platforms are generated for these different cases. So in the chair case, you can see this standing chair, then the little move chair. You can see how the platforms are moved and the robot achieves that with the goal. More examples of closing the cabinet and so on. All right, in the last part of the talk, I want to explore the third possible visual plan, which is the pixels themselves. Here there's been like huge advancements in generating videos using and generative video approaches. And so we want to see if we can use any off-the-shelf video generation algorithm and use that as a plan itself. Now here we are able to exploit the large-scale effort in this prediction. And the idea is that we can do these large-scale models can do a lot of heavy lifting. And then the robotic model can be actually very small and learn from different data sets. There's another benefit of going with pixel-based approach. You can also now chain these different actions into a big long horizon action itself. And I'm going to show some examples of that as well. So here are some of the examples, like given the drawer, open the cabinet drawer or place. Here's an example of place the apple in the drawer. And you can see these videos look reasonable enough, or pick up the tissue from the box. So we first generate, given the initial image and the task, we first generate a video. Then they convert this video into track points. And then we use track points to predict the robot action. Going to the approach is again very simple. Given the original video, we have these predicted track points. Given the generated video, we can predict track points by tracking them. And both this original video and the predicted track points from the generated video are used to learn the mapping between the track points and the actions. And so just the model looks something like this. So given this original image and the task, you first generate the video, generate the tracking track points from this. You generate from the original video also, you generate the track points. And now your goal is to learn representations that can not only do the task, like learn the mapping between the track points and the robot action, but also predict these track points. And so the hope is that by focusing, having these extra losses, the model can actually focus on the right things to learn the mapping between the track points and the robot actions. And as I was saying, one of the benefits of using these pixel-based visual plans is now you can, for the first time, chain these to create long horizon tasks. So for example, here's an activity of making a coffee. So you first predict, like the first step includes opening the lid. And now you basically look at the opening the lid video is being generated. Using the last frame as a first frame of the next task, you can generate the next part of the video, which is inserting the K cup. And this is the plan for inserting the K cup. Again, using the last frame of this sub video, you can now generate the next part, which is closing the lid. And then you can chain all these different actions into the final robot action as well. And you can do this long horizon task as well. Here's another example of cleaning the table. Again, you first basically figure out what are the subtasks like gather materials, supply sanitizer, and buy. Now you basically generate these different sub videos where the last frame of the video can be used as the first frame of the next sub video. And then you basically convert them back into robot action. For more experiments, you basically use the Google's video poet model. The RT1 dataset was used to convert into videos like these track points into actions, and the robot action space was end effector and so on. And here are some of these examples of like pouring from cup into the pot. So that is a generated plan in the middle, and then you are basically converted into robot action by mapping this video to the robot action. There is another example of wiping the table with a brush. And again, most of the heavy lifting is being done by the video model, and converting this track points into the robot action is a much simpler task, which we can learn with a much limited data set. Couple of more examples. And here are like some of the more detailed examples from lots of different scenarios. All right. So today, to conclude, I focused on how we can use videos and images on the web to scale up robot learning. The idea is that there is not enough robotics data to learn robotics foundation model directly. And so what we can do is we can use this passive data on the web, the large amounts of passive data, to scale up learning. And we focus on two ways. First is the pre-training. We can do pre-training of these models from this passive data and then learn the policy. And we also looked into if we can learn world models from this passive data and then only learn actions on the top of these world models, essentially. And the idea is that most of the heavy lifting will be done by this passive data approaches, and then you can focus on much smaller robotic action with much less data to actually build them to achieve the task. All right, with that, I'll end the talk.
Okay. Thank you, Abhinav, for the excellent talk. Any questions from the audience?
Abhinav, great talk. So what's missing? You've shown a lot of things that are working well, lots of videos of things that actually, successful. What is the big gap from your perspective in terms of turning those models into something where you can just say, we figured out the robotics problem, the nominal robotics problem is solved?
Yeah, I think this is the curse of robotics. I say whatever is the works of robotics, also the videos are the curse of robotics, because videos can give you a false pretension that things are working. Whereas in the real world, I think the biggest question is, like, for example, in the last part that I'm showing, again, these video generation models are not like, it will not work on every scenario. There are only very few scenarios these video generation models work. What I think what we are able to see with these video-based approaches is that the amount of generalization that you can get is much larger than if you were doing basic teleop like kind of approaches. So this passive data can improve your generalization a bit. But that said, I still feel the basic lower level actions like hard actions like open are still like dexterous action are still, there's a long way to go in the dexterous actions. And furthermore, I would say that the generalization still needs to go much further than what we are seeing even today. So in some sense, I would argue that these models are starting to generalize, but they're not robust enough to completely do. So in my view, we need another scale of robotics action data. This is a great start, like using these kind of VLM models and generative models to get some kind of a generalization. But what we are still missing is the next boost in the robustness of these actions, and which will come, I feel, from the next order of robotics data. I think we are still missing another order of robotics data in the manipulation space to actually achieve these goals.
Okay, thank you. Yeah.
Hi, and very good talk. And I was wondering for about the first part, when you train features with your MAE or like formats, how does it compare to, like using VLM features? So, I mean, I refer to VLA, you take the VLM, you put the diffusion and you fine tune it. What's the comparison?
Right. Yeah, that's a great question. So we have found that again, these VLM features, so we have not tried the latest one. This is a little like couple of years older paper. That point of time, there was not that many. But whatever we have tried off the shelf, whatever features that you can get like clip and so on, I think they are not still as good for robotics tasks as the ones that you can train with these affordance features and so on. So at that time, only clip was the one which was we compared to clip, and we did not find enough good features for robotic representation with clip as well and so on. These new brand of like, I think after that, there has been again significant work in this VLM space, like especially in the feature space and so on. So I'm not 100% sure how it would compare to that, but that would be a good approach to try again with these new VLM features. How would it do?
Okay, thanks for answering. Maybe one last questions. Yeah. As I know you're not going to participate in the debate question, so I will just raise one most related debate question to you here. So, as we know now that many video generation models are trying to make the generated results photorealistic, consistent across frames. Do you think that is necessary for world model to world models for robotics, or just latent action consistency, or we perform the future generation in the latent action will do for world model research in robotics?
Yeah,
yeah.
I think that's a great question. In fact, I mean, in a lot of my slides, this is not that version of the slides that I'm using today, but I actually argue that robotics should form as a benchmark for people doing world models.
Yeah.
Right. I mean, a lot of people who are doing world models of video generation today are mostly doing it for Twitter kind of a thing, which is fine. I mean, of course, Meta needs to generate, for example, advertising things and
like
so on.
Pixel level.
Yeah, pixel level kind of, but that's not from intelligence purposes. That is not the goal, to generate interesting videos or cute videos. Or, for example, if you're having errors in predicting the ceiling pixels, it does not matter.
Yeah.
Right, because it hardly you care about the ceiling pixels that much unless it's going to fall down or something like that, right? So what should be the right benchmark for pixel generation? It should not be the kind of benchmarks that everyone uses, like the PSNR and all that stuff and so on. In fact, this robotics could act as a big benchmark. If your video generation can actually help, or can actually help robotics tasks, then that means you are predicting the right things, like the contact points and so on, you are able to predict, right? Because if you think of actually the video generation models, this is exactly where they lack the contacts and the manipulation and the dynamics and so on. They're really, again, good at texture. The sad part is these approaches are also really good at texture, but not these contact dynamics and so on. And so in some way, I actually argue that robotics should form as a benchmark for all the video generation approaches. And unless they are improving in robotics task or something like that, like, or maybe it is a robotics task and simulation so that everyone can do it. But the idea is that unless it improves that means it's not a good video generation algorithm itself, for example.
Okay. Thanks for answering. Thank you. Let's thank again for Professor Abhinav for talk today. So, yeah.
I'm sorry for not attending the debate. I have a flight to catch.
Yeah, it's totally fine. So, we'll have our final section today. It's a debate panel. We have a lineup of speakers from today to join us. Yeah, let's set up some things for now. So yeah, you can come up to the stage. So yeah, we can get you seated here. And Christos will be the moderator of the debate section. We have several questions covering today's talks, language model, word models, photorealistic reconstruction, and so on. Is it necessary or not? So we have this question for you, and we'd like to hear your opposite argument or opinion on this kind of topics. Yeah, if you can form two teams or so, so we could see that what is the argument for each kind of size. So yeah.
So if we're gonna do this, can I ask the people in the audience to come closer?
Yeah,
Maybe
yeah.
to the first row, and maybe like,
Yeah.
can even put the chairs more closely and have a conversation. That would be a lot nicer. And then
Yes,
we're gonna
please
ask questions
come
like.
closer. It's easier to interact.
You can.
And we have prepared.
Yeah, we have prepared a seat upstairs, so
to-
Like maybe let's use those. Let's just use these ones.
we have like
Let's just set them up.
we have one here already. So should I still stay upstairs for the laptop? Yeah. Also, online and forward. How do you think that I should also come downstairs or how? It's okay, perfect. Okay. Let me try to establish some visual contact with panelists. All right, thanks to all the attendees for being here, and we hope to have a final interesting session to close the day. The idea is that we also want to involve the attendees via live voting. So we will start, we have some different questions. And the idea is that first, the panelists will each vote for the one of the answers by raising hands. And then the audience will also vote for one of the answers. And then we will have the different panelists that support one or the other answer to explain the rationale, and then we can also have some more open format discussion after the initial statements. So then the first question will be regarding what tasks and what variety of